Hello guys, we are going to do that makeup assignment now, which is we're going to be looking at stoichiometry today. So this is coming from the PowerPoint online that's called Stoichiometry. So if you want to download that, you can follow through this videos that I'm going to make. I'll have to make probably 2 videos, maybe 3, depending on time frame wise. But either way, we're gonna work through this together. You're seeing the screen that I have pulled up. You'll see little images of the PowerPoint slides as it is. So first thing we're gonna do is we're gonna look at the mole ratios, and then we're gonna talk about stoichiometry, and then we're gonna end up with percent yield. Now, before I get into this, I want to go through the second slide, which is the titanium production. Now, the question comes, and that is, where does titanium come from? Now, we may think there's many different places that it comes from, but there's only one place, and that's from a rock. As you can see here, we have an example of a mineral called anatase, and the formula for this particular mineral is titanium dioxide. Now, we're going to talk about the process, and this is what's going to lead us into our PowerPoint. We're going to talk about how production of titanium is done. So they take this mineral anatase, rutile, ilmenite. There are different forms of it, but they take this mineral and they have to extract the titanium. Now, if you notice in the formula, it's TiO2. What they do is they heat up this sample to a very high temperature, and basically what happens is they separate the two. They turn the titanium into a gas, and then the oxygen separates out from it also as a gas. Now, if you were to leave this and let it cool back down, the titanium would react with the oxygen and reform the titanium dioxide. So what they do is they take the titanium and they react it with chlorine gas. So they inject chlorine gas into this sample, and it forms titanium tetrachlorides, TiCl4. Keep in mind this is a very high temperature, so these are all gases here. So gas. Now the other thing we're going to pay attention to is the balancing equations part. So there's 4 Cl's on the right hand side, there's 2 on the left, so we're going to put a 2 in front of that. Now the last process, which is actually shown here, we're going to take Tickle, which is what this compound here is called. This is called Tickle. And we're going to react it with magnesium to form titanium plus the magnesium chloride. So this titanium tetrachloride is actually bubbled into this reaction vessel here. And since it's less dense, it goes up into the layer of magnesium and reacts with the magnesium, and then the titanium is coming out as a product. As you can see it here, it's coming out, and it falls, since it's more dense, it falls back out to the bottom, and this is where we collect our titanium. Now, first, before we do anything, let's balance this equation. So again, we see that there are 4 Cl's on the left, there are 2 Cl's on the right, so let's go ahead and take care of the Cl's. We're going to put a 2 in front of that. Now you also see when you do it, you have 2 magnesiums, so we're going to put a 2 in front of that magnesium there. So we're going to take this equation that we just balanced, and we're going to work with it. So we're going to go on to the next slide here. So the first question that we're going to answer is, what is a mole ratio? Alright, let's answer the question, what is a mole ratio? So a mole ratio is a ratio of the reactants and products that is dependent on the molar coefficients of the balanced equation. So we're going to look at a couple examples here. So what are the possible mole ratios for the reaction described below? So we have titanium tetrachloride, we have magnesium, titanium, and MgCl2. So we're going to compare tickel to magnesium just so you get an idea of a mole ratio. Now ratio is also going to be used as a conversion factor when working problems. So now if we want to write a ratio of tickel to magnesium, we'd say that there was 1 mole of tickel for every 2 moles of magnesium. That means that for every mole of tickel, we're going to need 2 moles of magnesium and vice versa. So this could be wrote the opposite way. So you have 2 moles of magnesium for every 1 mole of tickel. And so you can write the mole ratio for the product as well. And so it really just depends on the question that we're looking at in the problem. So now we're going to move on to the next slide here, as you'll see it being pulled up here, where we have a basic question that's being asked. So it says, if a scientist starts with 400 grams of magnesium, how many moles of tickel would he need to react completely with it? Now, notice that they say that you have 400 grams of magnesium. And they ask the question, how many moles of tickel are you going to need? So that you have to have a setup here. You have to figure out what pathway you're going to want to go. So now if you remember before, we talked about the road maps. You have grams to moles, you have moles into grams, and now we have a new one, moles of A converting into moles of B. Now if you pay attention here, we're going to start off with grams of magnesium. So we're going to convert grams of magnesium into moles of magnesium. So let's go ahead and take care of that. All right, so we have 400 grams magnesium. The molar mass of magnesium is, look at your periodic table there for a second, guys. So 24.31 based off of my periodic table here. And so we're just going to go to the second decimal place here. Now that's the first step. So in your calculators, go ahead and type in 400 divided by 24.31. That gives me 16.5 grams of magnesium. Now we want to figure out moles. So we're going to go from moles of magnesium into moles of tickel. Now we're going to use the mole ratio here. We know that there's 1 mole of tickel per 2 moles of magnesium. So again, the 1 comes from, pay attention up here, 1, and then the 2 comes from here. So you know where the mole ratio is coming from. So all we do now is we're going to take that 16.5 and we're going to multiply it by 1 and divide by 2. Which is going to give me 8.25 moles of tickel. always make sure you include your units. So that's the answer for that question. So, looks like we have a duplicate here. Let's move on to the third one, see what we got there. Oh, here we go. New problem. So now the next problem says if a scientist starts with 8.23 moles of tickel, how many grams of titanium will be produced? So now we're going to start off with moles, and you don't always have to start off with grams. You can start, this depends on the question. In this case, we're starting off with moles. We're going to convert that into grams of titanium. Now, it looks like we can go from moles to grams, but that's not what we need to do. What we need to do is convert moles of tickel into moles of titanium, and then that converts into grams of titanium. So there's two calculations here. All right, so let's go ahead and do it. So we got 8.23 moles of tickel. We're going to multiply by 2 moles of, well, scratch that. We have a different problem in my head. Let's do it. Okay, here we go. Now we're going to multiply that by 1 mole of titanium per 1 mole of tickel. Now, this is a 2-step problem, so I'm going to extend this T-chart out to one more step here. So we need to look at the molar mass of titanium. The molar mass of titanium is 48 grams per mole. I did a little rounding there, but it'll be okay. You guys keep your decimal places when it comes to the test. So, alright, all we got to do now is we're going to take 8.23. Since we know multiply by 1 and divide by 1 is going to give you the same answer, we're just going to go ahead and do 8.23 times the 48. And you end up with 395 grams of titanium. Alright, so we're going to stop the presentation of this video. In the next video, we're going to talk about percent yield and possibly limb reagents.